Hey everyone, welcome to the third video for section 7.5. So in this video we're just doing some examples of solving ODE systems that have constant coefficient matrices where there are two real and distinct eigenvalues. So we're going to set up a couple matrices, do the examples, sketch out the phase portraits, and show you what those look like. Let's go ahead and jump right into the examples. Example 1. Find the general solution and draw a phase portrait for the system x prime equals 7, 2, minus 3, 2, x. All right, so how do we start? We gotta start by finding the general solution, so we need to find the eigenvalues and then find their corresponding eigenvectors. So 1, look for eigenvalues. So for this, we take the determinant of the matrix here, we subtract an r along the diagonal. So 7 minus r, 2, minus 3, 2 minus r, which is 7 minus r, 2 minus r, plus 6. So here I get a 14 minus 9r plus r squared plus 6, which turns into r squared minus 9r plus 20, which factors as r minus 5, r minus 4. So my eigenvalues are 4 and 5. Step 1. Now, step 2, let's find the corresponding eigenvectors. For r equals 4, so I want to look to make sure it had the r's in it. So if I scroll back up, it was 7 minus r, 2, minus 3, 2 minus r. So if I plug in r equals 4 there, I get 3, 2, minus 3, minus 2, times x1, x2 equals 0. I can now write this as a linear system. So I get 3x1 plus 2x2 equals 0, minus 3x1 minus 2x2 equals 0. And again, the second guy is redundant. It's just negative the first one, so I can ignore him. And this tells me if I set x2 to be 1, then x1 equals negative 2/3. Just by plugging 1, move to the other side, divide by 3, that's what I get. So negative 2/3 1 is an eigenvector for my matrix, which I'm just going to say is A, with eigenvalue 4. Good. Now let's look at r equals 5. If I do the same matrix thing, I will see 2, 2, minus 3, minus 3, x1, x2 equals 0, which gives me the two equations, 2x1 plus 2x2 equals 0, minus 3x1 minus 3x2 equals 0, and yet again, redundant as it should be. So this here tells me x1 plus x2 equals 0. So if x2 equals 1, x1 equals minus 1. So minus 1, 1 is an eigenvector for A with eigenvalue 5. So I had 1 for 4 up here, 1 for 5 down here. So now I can write my general solution. So general solution is x of t is c1 times the vector negative 2/3 1 e to the 4t plus c2 the vector minus 1 1 e to the 5t. Now I got that just by plugging in the eigenvectors and eigenvalues I found before. So I'm going to scroll back up again for a second. I had that 2/3 1 was an eigenvector with eigenvalue 4. So in my solution, I have a negative 2/3 1 e to the 4t. And I had minus 1, 1 as an eigenvector with eigenvalue 5. So in my solution, I have a minus 1, 1 e to the 5t. So that's how we get our general solution for this problem. Now I want to do the phase portrait. I'm going to leave that right there. All right, so step 1 was drawing the straight lines that we know are solutions. So I know 1, 1 is going to be right here. So this is going to be along, this is going to be, I'm just going to raise the vector minus 1, 1 to know what I'm talking about. It's the vector along that line. And then minus 2/3 1, which is going to be a little bit steeper. This is here is minus 2/3 1, is that vector. And I notice that in both cases, my coefficients are positive, which means in all cases, I'm running away from 0, from the origin. All right, And now if we look at this, what we see is, since 5 is bigger than 4, as t goes to infinity, this term matters more as t goes to infinity. But this term also blows up. So it's not going to 0, it's going to matter less. Which means, so the orange stuff over there, I want to leave room so I can draw curves in here. But the orange stuff there means curves go parallel to -1, 1 as t goes to infinity. Now, on the other hand, as t goes to -infinity, this stays up longer as t goes to -infinity. So what that tells me is all curves come to 0 tangent to -2/3, 1. Because the other term is going to 0 as t goes to -infinity. So as t goes to +infinity, all curves are going to go parallel to the -1, 1 line. And as t goes to -infinity, all curves are going to come into 0 tangent to the other line. So what does that mean? So if I start at this point here, I have to come into 0 as t goes to -infinity, tangent to the -2/3, 1 line. So I have to come into 0 sort of like this. I'm coming in tangent to this line. And as t goes to infinity, I have to go off parallel to the 1, 1 line. So I'm going to stay over here and sort of go this way, assuming that line is straight. Now remember, we're dealing with first order solutions here, which means our curves can't cross each other. So we can't like jump over to the other side of one of these lines. We have to stay separate, stay where we were before. So if I'm here, I'm going to come in this way and take off like this. And I can have one up here that sort of does it on a bigger scale like that. Nope, but the arrows are all going out. Similarly, if I'm over here somewhere, I have to go off to infinity parallel to the 1, 1 line, but I have to come into 0 tangent to the -2/3 line on my appropriate side, because I can't switch sides of these lines. And in between here, I'm doing the same thing. If I'm starting at this point here, I have to come into 0 tangent to this line and go off to infinity parallel to this one. So something like that. And in here, we're doing the same thing. I have to come out along this one and go off parallel to this one. So a lot of this is guesses. A lot of this is going to be guessing. But it gives you an idea of what's going to happen to the solution as time goes on. Basically, draw in the two solutions you know, figure out what their behavior looks like as t goes to plus and minus infinity, and then fill in the rest from there. All right, example 2. The problem's the same, but the matrix is 1, 2, 2, 1 instead of what we had before. So step 1, eigenvalues. Determinant of 1 minus r, 2, 2, 1 minus r equals 0. So I get 1 minus r, 1 minus r minus 4. R squared minus 2r plus 1 minus 4 is r squared minus 2r minus 3, which factors as r minus 3, r plus 1. So the eigenvalues are minus 1 and 3. And now we look for eigenvectors. So r equals minus 1 gives me, I'm looking to solve, I plug in minus 1 for r, 2, 2, 2, 2, x1, x2 equals 0. And now I obviously only need to write one of these equations, so 2x1 plus 2x2 equals 0, or x1 plus x2 equals 0. So if x2 equals 1, x1 equals minus 1. So minus 1, 1 is an eigenvector with eigenvalue minus 1. And I can look at 3 as well. So r equals 3, minus 2, 2, 2, minus 2. x1, x2 equals 0. And again, only writing one equation, negative 2x1 plus 2x2 equals 0. Negative x1 plus x2 equals 0. So if x2 equals 1, x1 equals 1. So 1, 1 is an eigenvector with eigenvalue 3. So then what is my general solution? Well, if I put all of this together, I get x of t equals c1 negative 1, 1 e to the minus t plus c2 1, 1 e to the 3t. Again, c1 eigenvector 1 times e to the eigenvalue 1 plus c2 eigenvector 2 e to the eigenvalue 2t. All right, phase portrait. Let's start with our straight line solutions. So I know I have one that goes to 1, 1 up this way, and one that goes to minus 1, 1 this way. Again, assume those lines are straight, but I can't really draw on here. And now we look at directionality. Now, for 1, 1, that has a positive exponent. So this one is going away from the origin, but minus 1, 1 has a negative exponent. So that one's going to come in as t goes to infinity. From that, then, it's easy to see that this term matters as t goes to infinity, and this goes to 0 as t goes to infinity, which means all curves approach the 1, 1 line as t goes to infinity. And then we get the reverse the other way. This goes to infinity and matters as t goes to minus infinity, and this goes to 0 as t goes to minus infinity. So all curves approach the minus 1, 1 line as t goes to minus infinity. So what I get are curves that say I start here. I'm going to go and approach this line as t goes to infinity. I'm going to approach this line as t goes to minus infinity. Over here, this way as t goes to infinity, this way as t goes to minus infinity, and then same thing here and over here. This is the one I showed in one of the videos previously, something like this. So that's what your phase portrait looks like for this kind of system. Now, this guy here is called a saddle point. That's kind of what it looks like, right? From one side you're coming in, from the other side you're coming out, it's a saddle point. And this guy is unstable. Because if you look anywhere nearby 0, everything's going to run away. Unless you're on that one line that goes into 0, everything just goes away. So it's an unstable critical point. If we go back up to the example from the previous video, or the previous example, depending on if I cut them into 2 videos or not, this is what's called a nodal source. Because every curve goes out of the center. Right? It's a node because everything's coming out of it and going the same direction, but it's a source because they're all coming out. And this guy is also unstable. The other example is one that I haven't done, but if you had R1 and R2 both negative, then you get what's called a nodal sink, which would look just like the one you see right here, but everything would be going in instead of going out, and that one is stable. So your 3 types for real and distinct roots are nodal source, nodal sink, and saddle point, the nodal sink being the only one that's stable, asymptotically stable, the other ones are both unstable. All right, so that's it for the examples. Hopefully that made sense, and you can sort of use this to solve the other problems that I gave you to do and be ready to do more of these in class tomorrow. All right, thanks for watching, and I'll see you in the next one.